All right, problem one of the simple harmonic motion review guide. You got a pendulum there, and the picture has it oscillating between 3 points. Those 3 points are labeled A, B, and C. It's going to go back and forth, back and forth. We are told that the length of the pendulum from here to here or here to here, the length is 0.25 meters or 250 centimeters. And then the mass that's attached to it is 0.40 kilograms, or 400 grams basically. First thing we're asked to do is calculate the expected period of the pendulum. Now, this is a classic mistake that a lot of people are going to make here. When you are looking at your formulas, you see this formula here, 2 pi L over G, and you also see this, 2 pi square root of M over K. And when we're looking at those two formulas here, a lot of people go, look, I have a mass, let me put it in there. But you got to remember, this is for spring, whereas this is for a pendulum. This is the formula we want to look at. And you know what? The mass, it actually doesn't matter. This could be whatever it wants. The length of the pendulum is what's going to matter here. So we have the length. We can easily calculate the expected period here. It's going to be 2 pi square root of L, which is 0.25 over 9.81. You want to evaluate that out. Don't leave your answer in terms of pi. A lot of times your math teachers would like it if you did that. But in physics class, if we're looking for a a numerical value here, so that's pretty much what we'll do. I would say all throughout, I would say the entire class is always get out of pi there. So 2 pi times square root of 0.25 divided by 9.81 gives me 1.003 seconds. So I'll round at that point there. It's probably a reasonable place to round. And the next thing we're asked to do is find the frequency. You have two options here. You can actually use the formula, which I didn't put at the top of this review guide, but you saw it in the video. The inverse of the period formula would be this. 1 over 2 pi times square root of G over L. And you can put your numbers in for L and for G, and you can get your frequency. I find that most people will always screw up mathematically this operation here. You got to put it in parentheses if you're going to enter it into your calculator. Be aware of that. Your other option is to simply go 1 over the period. That's probably the route that I'll go here. But if you use that, you should still get the same answer. So when I do that, I get like 0.997. And if you recall, frequencies measured in hertz. There's our frequency. How much time would it take to go from point A to point C? Got to be careful here. A lot of people confuse what the period is. The period is the amount of time it takes to do one full cycle. That's from point A to point C. That's only half the cycle. A full cycle would go all the way back to the starting point here. So what we're talking about is basically half the period here. So I'm going to simply take the period and divide it by 2 here. That's going to get me points A to C, the time it takes to go from point A to C. So 1.003 divided by 2, putting that in there, would give me 0.5015 seconds. Alright, so you get exactly half the time that we would get for one full cycle. How much time would it take to do 5 full oscillations? So one full oscillation is all the way from A to C, and then all the way from C to A. You want to do that 5 times? All we're going to do is multiply the period by 5. So if we do 5 times the period here, it would be 5 times 1.003, which ends up being close to 5 seconds, but we'll get 5.015 seconds there. So, put that into perspective. We're not using formulas here, we're using kind of common sense. So you'll be expected to do that on whatever assessment I end up giving you on Friday. If the pendulum was pulled halfway back between point A and B, would that affect the period? You got to be careful here. This is a very common thing that's hard to wrap your head around, but I mean, you should have kind of seen it in my demo and also in the simulations here. What if we only put it back to here and let it go that way and then that way? It's got a lot less distance to cover, but interestingly enough, it doesn't affect the period. You can't affect the period without changing the length. That's why a pendulum clock actually works the way it does, because the pendulum clock may run out of energy over time as it goes less and less and less and loses energy to friction, but the length is the length, and so that can't change the period of the oscillation because the length is a constant value here. So the answer to E is no. L is all that matters. That would be my justification, and you can see that in the formula. There is nothing in the formula as to how far back we pull it. Would attaching a larger mass to the pendulum affect the period? We've discussed it already, but since we're looking at this formula here, you see nothing in there for mass. The length is all that matters. So again, I would say E and F would have the exact same answer here. L is all that matters. So let's stop it there for question 1. We'll do question 2 in another video.